Hello guys, welcome to my YouTube channel Vishwaguru, a problem solver. Today's class we are going to discuss a numerical on the topic analysis of perfect frames by using method of joints and method of sections. That means by using both the methods, this numerical we are going to solve. Let's go to the numerical. The figure shows a Warren girder consisting of 7 members, each of 3-meter length, freely supported at its endpoints. The girder is loaded at B and C as shown. Find the forces in all the members of the girder, indicating whether the force is compressive or tensile. Here, a frame structure is given. Point A and D, it is freely supported. Okay. And then at point B and point C, it is loaded as shown in figure. Okay. At point B, 2 kilonewton point load is acting. At point C, 4 kilonewton is acting. Here you can see the 3 triangles. Each triangles are equilateral triangle. All the angles are equal to 60 degree. That means we can say all the sides equal to 3 meters, because between A and D, that is 6 meter. Then from the angles, we can identify AE, that equal to ED. That means all the lines or all the members has same length. Here, that is 3 meters. Okay. So AE, ED, everything 3 meters. So first thing, by using method of joint or method of section, whatever, if it is a simply supported frame, like given in the diagram, first thing, we have to calculate the reactions. Okay. So first thing, the reaction calculation. Okay. In reaction calculation, we will calculate by using equilibrium principles. Among the equilibrium, 3 equilibrium principles, we will use 2 principles, such as summation of vertical zero here, summation of moment about any point, preferably from the point A, and equate that to 0. Okay. Because here there is no horizontal forces. So first we are going to consider the vertical forces. Okay. Summation of vertical forces equal to 0. Here, there are 4 vertical forces are there. RA and RD. The 2 forces are acting upward. 2 kilonewton and 4 kilonewton. That 2 forces are acting downward. So we can write RA plus RD, that equal to 2 plus 4. So we can write RA plus RD, that equal to 6 kilonewton. Okay, this is equation 1. Then take moment about any point, preferably from the point A, and equate that to 0. Okay, because if this 7-member structure is in equilibrium, then moment about any point should be equal to 0. Okay. When you take moment about A, the moment made by the force or A, which is acting exactly at the same point A, that can be eliminated. So when you take moment about A, the moment made by the other 3 forces we have to consider. And then here you can see the 2 kilonewton is acting at the point B, but as per the principle of transmissibility, the force can be considered at points anywhere in the line of action of force. Okay. So this 2 kilonewton can be considered is acting at this point also. Okay. So here you can see this I'm going to consider F. And then we know that if all the members having each 3 meter length, and then if it is equilateral triangle, this AF, that will be half of the length AE. So this will be 1.5, this will be 1.5. Okay, that means this dimension will be 1.5. Okay, this dimension will be 1.5 meter, and each segments like this we will get 1.5 meters. Same way, this point C, this also considered acting anywhere in the points, anywhere in the line of action of the force. So this 4 kilonewton can be considered at this point. Okay, that means G also. So when you split this, all the segments will become 1.5 meters. Okay, all these segments will become 1.5 meters. So here, when I'm going to take moment about the first point A, the moment made by the reaction upward force, that will be eliminated. Then we can say this 2 kilonewton, which is acting along the point B or point F. Okay, it will be a downward force here. With respect to the point A, this 2 kilonewton multiplied with 1.5. Okay, that will be in clockwise direction. So 2 multiplied with 1.5. Okay, plus this 4 kilonewton is acting at the point G, and the point G is from the reference point at a distance 1.5, 1.5, 1.5. That means 4.5 meters. So this 4 kilonewton, okay, 4 kilonewton multiplied with this 4.5. This is also in clockwise direction. Okay, so 4 multiplied with 4.5. This is also in clockwise direction. This will be counterbalanced by moment made by the upward force, reaction force RD, multiplied with 6 from the reference point A. This will act in counterclockwise direction. Okay, so RD multiplied with 6. Okay, on the left hand side, clockwise moment, right hand side, counterclockwise moment. Okay, so from this, if you simplify, we will get the value of RD. Okay, that equal to 3.5 kilonewton. Okay, that equal to 3.5 kilonewton. If you substitute RD equal to 3.5 here, then we will get RA equal to 2.5 kilonewton. Okay, so both the values here we calculated. So now we are going to start the method of joints or method of sections. Okay, so first I'm going to consider method of joints. Okay, that means there are 3 principles are there in equilibrium. Summation of horizontal forces equal to 0, summation of vertical forces equal to 0, summation of moment about any point equal to 0. In method of joints, we will use the first 2 principles, summation of horizontal and summation of vertical, that equal to 0. Okay. First, I'm going to start with the joint A. Okay. As I mentioned in the previous numericals, we are going to start with the corners, the joints from the corners. So the first joint A. Okay. In joint A, there are three forces are acting. The free body diagram of the joint A. Okay. The vertical upward force, reaction force, RA is acting, and an incline force, that is the tension or force in the member AB is acting. Then a horizontal force, that is tension in the member AE is acting. This inclination is 60-degree. Here, the upward force RA, that is 2.5 kilonewton, magnitude and direction of the force RA, that is known. The magnitude and direction of these other two forces, tension in the member AB, tension in the member AE, that we have to calculate. Okay. So here, first thing, here I am going to consider the principle, that is summation of vertical forces equal 0. Here you can see, if this entire object or the truss member or frame that is in equilibrium, each joint should be in equilibrium. So all the forces, that means here there are three forces are acting at point A. Then when you calculate that means when you use the equilibrium principles here, that should be satisfied. Okay. Like summation of vertical 0, summation of horizontal 0, or summation of moment about that point equal to 0. Okay. So here there are three forces are there. RA is the upward force, upward or vertical force. Okay. Here the another force TAE, that is a horizontal force. So that cannot compensate this RA. Okay. So the only the other forces, that is TAB, that is an inclined force. Here the TAB, there are two possibilities are there. Both the possibility here I am going to mention for the first joint to understand it very clearly. If the TAB, the tension in the member, the possibility 1, if it act away from the joint A or outwards from the joint A, it will act in the first quadrant. Then we will resolve this into two component, that is TAB cos 60, the horizontal component that will act towards right side, that is positive X direction. The TAB sin 60, that will act in positive Y direction. Okay. But here you can see this RA, that should be counterbalanced by the vertical component of the inclined force TAB. That means by using TAB sin 60-degree, the RA should be counterbalanced. If this TA is acting like this in the first quadrant, the vertical force TAB sin 60, that will act vertically upward. So here RA is an upward force. To compensate an upward force, we need a downward force. Okay. But if this TAB is acting in first quadrant, then TAB sin 60 is also upward. That cannot cancel the upward force RB. So this possibility, that means this can be eliminated. Okay. So now I'm going to mention the second possibility. That is the TAB is acting inwards to the joint A. Okay. That means this will act in the third quadrant. If it is acting in the third quadrant, then we can say that means as per the line of action of force, it is acting like this from the joint A. So this will be the vertical component, that is TAB sine 60 degree, and this will be the horizontal component, that is TAB cos 60 degree. Okay. So here you can see if this act like this, then the vertical component that will be downward that can compensate the RA. Okay. So this will be the possible condition. Okay. So summation of vertical zero means RA, the upward force, that equal to TAB sine 60 degree. Here we know the value of RA sine 60, that is also we know. So from this we can get the value of TAB, that is the tension in the member. Okay, that we will get 2.887 kilonewton. Okay, 2.887 kilonewton. That means here this going to act inwards to the joint A. Then same inwards to the joint B also. So the forces, tension forces in the members AB, that tend to pull the member AB. So this will be tensile in nature. Okay. So TAB we calculate. Then tension in the member AE. Here you can see when you consider the TAB, that force is acting inward to the joint A, then the horizontal component, resolved component of the inclined force TAB, that will act towards left side. So this left side force should be compensated by the right side force, that is TAE. So here summation of horizontal forces equal to 0. So we can write TAE that equal to TAB cos 60 degree. Okay, this TAE that equal to TAB cos 60 degree. Here already we calculated the value of TAB. If you substitute the value, we will get the tension in the member AE that equal to 1.444 kilonewton. Okay, here you can see from the joint A, it is acting away from the joint. So from point E also it is acting away from the joint. Then we can say this AE, the forces in the member AE, that is compression in nature. Okay, that is compression in nature. Okay, so as of now, we calculated the forces in these two members, AB and AE, by considering the method of joints in the joint A. Okay, so remind 5 members we have to calculate. After that, we are going to consider the joint D. Okay, next we are going to consider the joint D. Okay, so here the joint D, there are 3 forces are acting. I just draw the free body diagram of the joint D. From the joint D, an upward force, that is the reaction force, RD is acting. This inclined force, that is force in the member, tension in CD, that is acting. The horizontal force, the tension in the member DE or ED, whatever that is acting. As usual, the RD is the magnitude wise and direction wise known value. The value of RD that equal to 3.5 kilonewton, RA 2.5 kilonewton, that we calculated already in the reaction calculation. So here, when I consider summation of vertical forces are equal to 0, RD is an upward force. The same way, this cannot be compensated by the horizontal force TDE. So only by using the vertical resolved component of this inclined force TCD, which is acting 60 degree to the horizontal, that vertical component only can resolve this RD. Here there are two possibilities there. It may act in fourth quadrant. If it acts fourth quadrant, then the TCD, I just to draw the free body diagram of the TCD alone. Okay, the TCD, then the vertical component TCD sine 60 will act downward. TCD cos 60 that will act towards right side. Okay, so here you can see if this TCD is acting away from the point D, then it will, that means the vertical component will act upward, that cannot cancel RD. So this should act like this. That means inwards to the joint D. Okay. So now you can see summation of vertical forces equal to 0. The upward force RD that will be compensated by the downward force TCD sine 60. We know the value of RD. So from this, we can get the value of TCD. Okay, that equal to 4.042 kilonewton. And then here, for the point D, it is inwards. Then for point C also, it will act inward. So the force in the member TCD that will act tensile in nature. Okay, that is a tension force. Now summation of horizontal forces equal to 0. Here you can see when this TCD is acting in fourth quadrant, the horizontal component TCD cos 60 that will act towards right side. So this right side force will be balanced by the left side force TDE. So the TDE that equal to TCD cos 60 degree. Here the TCD value we calculated already, that is 4.042 kilonewton. From this we can calculate the value of TDE that equal to 2.021 kilonewton. And then here you can see from the point D, it is acting outwards. Then from point E also, it will act outwards. So this ED, the force in the member ED, that tend to push or compress the body. So it will be compression in nature. Okay. So up to this, we calculated for the joint D also. Okay. Then we are going to consider the joint B. Okay, next. So here B, I'm going to draw the free body diagram of the joint B. Okay, so here you can see this is point B. Here 2 kilonewton vertical downward force is acting at point B. Then there is a horizontal force, that is tension in the member BC is acting. And here we calculated already the incline force. And for the joint B, the tension in the member TAB, that is acting inwards. So the direction of this force also we know. And this will act with respect to the horizontal 60 degree. Okay. And then this is another one incline force, that is tension in the member BE. This is also acting at an angle 60 degree with respect to the horizontal. But the direction and magnitude of these two forces, tension in the member BC, tension in the member BE, these two is not yet calculated. This only we are going to calculate. Okay. So here, as usual, first I am going to consider the summation of the vertical forces equal to 0. Okay. So here, there are three possibility of the vertical forces. 2 kilonewton, that is a vertical downward force. This tension in the member AB, it's an inclined force with an angle 60 degree with respect to the horizontal. So when you resolve this TAB, we will get TAB cos 60 degree. That will act towards right side because this is in first quadrant, and TAB sin 60, that will act exactly upward. Okay. So here you can see the next incline force, that will be TBE. But here there are two possibilities as I mentioned earlier. This may act either upward, that means towards the joint B, or away from the joint B. Okay, that we have to calculate. Okay, so here you can see the summation of vertical forces 0. This 2 kilonewton, that is a downward force. Okay, and this TAB sin 60, that will be an upward force, that I'm going to take as minus TAB sin 60 degree. Okay, this downward force and this one is the upward force. So here, which one is a compensator? That means which one is the greater, that we are going to consider. Here the TAB value, that we know that 2.887 multiplied with 0.866. Okay, we will get 2.5. Okay, that is 2 minus 2.5. So here, this negative value is more. That means the upward force, that is having more value. So to compensate this, we need a downward force. Okay, so here only the possibility of inclined force is TBE. If it acts towards B, that means like this, then we know that the resolved component, that it's a vertical resolved component of TBE, that will be vertically upward. So that cannot cancel this. Okay, so this should act downwards like this. Then the TBE, we will resolve into two component like this. Okay, so this will be TBE, this will be TBE cos 60 degree, and the vertical downward component will be TBE sin 60 degree. Okay, so here this is 2, the downward force, minus TAB sin 60 degree. It is an upward force. So this TBE sine 60, that is also a negative force. Okay. So we can write minus this value TBE sine 60 that equal to 0. Okay. TBE sine 60 that equal to 0. Okay. So we know that already 2 minus 2.5 minus TBE sine 60 degree that equal to 0. From this, if you simplify, we will get the value of TBE, that is tension in the member BE, that equal to 0.577 kilonewton. Okay. And then here you can see the tension in the member BE from the point B, it is acting outward. Okay. So the same way from the point E also it will act outward. So the force TBE in the member BE, that is going to compress this. So we can write this as, this is in compression. So we can write it is compressive in nature. Okay. Then here now the TBC, that is one unknown force. Here all the three forces are in known direction. Okay. So the TBC direction and magnitude we can calculate. Okay. Here the horizontal forces TBE cos 60, that is acting towards right side. TAB cos 60, that is also acting towards right side. So the unknown horizontal force TBC, these two are acting towards right side. This should act definitely towards the left side to compensate the addition of these two horizontal forces. Okay. So here we can write by using summation of horizontal forces equal to 0. So the tension in the member BC, okay, that means this one, that equal to addition of these two horizontal forces, TAB cos 60, TBE cos 60. Okay, so that equal to TAB cos 60 degree plus TBE cos 60 degree. Now we calculated the value of TBE. Already we know the value of TAB. So if we substitute the values of TAB and TBE, then we will get the value of tension in the member BC, that is 1.732 kilonewton. Okay, 1.732 kilonewton. And then here you can see from the point B, that means to the point B, the tension in the member BC is acting inwards. Okay, so it is acting inwards to the B. Same way it will act inwards to the joint C also. So this will be tension in nature. Okay, this will be tension in nature. Okay, then we have to calculate the only unknown force in the member, tension in the member CE. Okay, that is force in the member CE. That is the only one unknown. For that, we are going to consider the joint C. Okay, next we are going to consider the joint C. Okay, so here in the joint C, what are all the things we are going to consider? This is joint C. Here, how many forces are acting? First thing, this point load, 4 kilonewton is acting. Tension in the member, that is the horizontal force, TBC, that is acting towards left side, inwards to the C. This force in the member TCD, it is acting like this. This is the unknown force, magnitude, and also the direction, that is TCE. This only we are going to calculate. Okay. So here, I just resolve this TCD. Okay. Here, this is TCD with an angle 60° with respect to the horizontal. So, the vertical component of TCD that will act upwards, TCD sine 60. The horizontal component will act like this towards left side, TCD cos 60°. Okay. Then, when you resolve, that means summation of vertical forces that equal to 0. Here you can see 4 kilonewton. That is the downward force. And then the TCD sine 60, that is an upward force. First, I just to put the upward force, that is TCD sine 60° minus the downward force 4 kilonewton. Here, the value of TCD that equal to 4.042, then multiplied with 0.866, we will get 3.5 for this value minus 4. Okay, here the 4 is the downward force. Here you can see comparatively the downward force is greater than the upward force. So this TCE that should act upward, okay, then only this can compensate the downward force, okay, or the resultant of these two forces. Here, the downward force that is greater than the upward force, so this should act in such a way that the vertical component will act upward. Okay. If this act like this, inwards to the C, then the resolved component, that is, if it act like this, then that means the TCE, if it act in first quadrant, the TCE cos 60°, that will act towards right side. TCE cos 60°, sorry, sine 60°, that will act exactly upward. Okay. So if you put that TCE sine 60°, the upward force as plus TCE sine 60°, it's an upward force that equal to 0. So plus TCE sine 60 that equal to 0. From this, we can get the value of TCE as 0.577 kilonewton. And here, the TCE, it is acting inwards to the joint C. Same way, it will act inwards to the joint E also. Then here you can see this is tensile in nature, that is tension. So now the forces in all the members we calculated. Okay. As of now, we completed the numerical. That means we found all the values. That means the forces in all the members. Now finally, we are going to tabulate the results. Okay. That is, I am going to draw the force table. That is the final results. Serial number, then members, then magnitude of the force, in terms of kilonewton. Then nature of the forces. Okay, nature of forces. So here, first of all, 1, the force in the member, that is AB. The magnitude we calculated as 2.887 kilonewton. And here you can see the forces in the member AB that tend to pull the body. So that will be in tension. That is tensile in nature. Then 2, that is force in the member AE. Numerically, we got the value 1.444 kilonewton. And then here you can see AE. This tended to push the body. So we can write this is compressive in nature. That is compression. Okay. Then the third one, CD. We got the numerical value 4.042. And here you can see this is CD that also tend to pull the body. So that will be tensile in nature. That means that is also tension. Then the fourth one, that is DE. And the magnitude of the force we calculated 2.021 kilonewton. And here you can see the DE that also tended to compress the body. So that will be compressive in nature. Okay. That also compression. Okay. Then the fifth one, BE. We calculated the numerical value 0.577 kilonewton. Here this is BE. Here you can see these two forces in the member tend to push the body. So that also compressive in nature. Okay, that is compression. Then sixth one, that is BC. We calculated the value 1.732 kilonewton. Here in BC you can see that is tensile in nature. So that is tension. Then the last one, that is CE. We calculated the magnitude of CE, that is 0.577 kilonewton. And here you can see the CE direction, that is also tensile. Okay, that is not mentioned here. That is CE also tensile. So that is also in tension. Okay. So I hope you all understand this video. Don't forget to subscribe my YouTube channel, Vishwa Guru, a problem solver, for more videos. And guys, as of now, we completed this numerical by using method of joints. Okay. The next video, that will be the part 2 of this one. The same numerical we are going to solve by using method of joints. Okay. Okay, guys. Thank you. Thanks for watching.